So today I'll be presenting Stardust, and that's joint work with Gabi, Bracha, and Golan Schzukin from Broadcom. So what do you think about when you're thinking about network switches? You might be thinking about switch silicon. And switch silicon today reaches 12.8 terabit per second. That's 32 ports of 400 gig. You might be thinking about a switch box that has one or two or several of these switch silicon devices, or even a switch chassis with several line cards and fabric cards. But then again, we have even bigger network switches. We've got network switch systems, such as the Cisco CRSX and Huawei 12800. And these multiple racks of network equipment reach a scale of a petabit per second. But then again, we have even bigger network switches, and that's data center networks. And they connect tens of thousands to hundreds of thousands of servers. And the question here today is, do these data center networks scale? So if I'm looking on a FAT tree topology, and I'll be focusing on FAT trees today, then I have the packets coming from the host to the top of rack switch using 40 gig links, 100 gig links, and from the top of rack switch going to the aggregate layer, that's the first tier, and then to the spine layer, that would be the second tier. And it will be using 100 gig ports or 400 gig ports. I will be referring to this entire part of the networks from the uplink of the top of rack switch and everything on top of it as the network fabric. And when I'm looking on 100 gig ports, they will be the aggregation of either 2 times 50 gig or 4 times 25 gig. If I'm thinking about a 400 gig port, it will be 8 times 50 gig. That's what I call a link bundle. A link bundle of 8 is 8 times 50 gig. A link bundle of 4 means 4 links of 25 gig. Okay? That's the number of physical links required to create a port. So how does the network, data center network scale? Let's look at an example of building a data center with 100,000 servers. If I assume that I have 40 servers in each rack, I'll need 2,500 top-of-rack switches. So if I'm using 6.4 terabit switches within this network, I can use 256 ports of 25 gig per switch. And then I'll need 2 tiers in the network and about 1,200 fabric switches. But if I'll decide to use 100 gig ports, I'll need 3 tiers within the network. And I'll need 66% more switches. And in general, the way that it scales is inverse proportional to the link bundling power, the number of tiers. So if I'd like to build a network using just 2 tiers, I can build using a link bundle of 1, a network with 64 times more hosts than if I use a link bundle of 8. So using 50 gig links, I'll be able to connect 64 times more hosts than using 400 gig ports. So that's our first observation. Using a link bundle of 1 enables us an optimum build of the network, less tiers and less switches. Now let's go back to the network switch silicon. A decade ago, if I wanted to design a new switch, I had, that's a good idea, maybe I should implement this feature, how do I implement it? Today I might be saying, well, that's a cool feature, but is it worth implementing given all the design constraints? And network switch silicon today is many billions of transistors inside. So 5 years ago, there was the Tomahawk device with over 7 billion transistors. To give you a base for comparison, the Xeon E5 V3 from around the same time had only 5.56 billion transistors. So that's a lot. And the switch silicon is limited by power density, by the size of the die, and by manufacturing feasibility. You don't want to manufacture a device that has a yield of 1%. So if resources are so important, do we use them wisely? Let's look again at our fat tree. If I have a packet coming in, it goes through 5 hops. I've got the edge, I've got the aggregate switch, the spine, the aggregate again, and the edge. And in each and every hop, I go through the I/O. I've got the network interface, which has a mark of 40 gig, 100 gig, 400 gig, and the network device will probably support all of them. I've got ingress processing, I've got egress processing, I've got queuing and switching in each and every hop. Now let's compare that to a switch system. In a switch system, a packet that comes in and needs to go from port number 1 to port 1000 will also go through 5 hops. It will start at a line card, go through a first stage fabric card, a second stage fabric card, a third stage fabric card, and go out through the line card. But look at the network switch that I'll use within the fabric card. It will be a lot simpler. It won't have the ingress processing. It won't have the egress processing. It won't have the queuing. And the network interface will be a lot simpler because I won't be supporting all these different types of marks. So why waste resources? In a network with n tiers, why do I need to do the ingress processing and the egress processing and the queuing n times? It's not just a waste of resources, it's also a waste of time. So we can save significant resources by simplifying the data center network. Let's go back to our switch. We've got 12.8 terabit switches. Woohoo! What does it mean? How many packets per second do we need to support? If I'm talking about 256-byte packets, that's 5.8 billion packets every second. If I'm talking about 64-byte packets, that's over 19 billion packets every second. But the clock frequency within these silicon devices is in the range of 1 gigahertz. That means that each and every clock cycle, I need to process 6 packets or 20 packets, okay? To support full line rate for all packet sizes, this means that network devices need to process multiple packets each and every clock cycle. We've reached the age of multi-core in networking. Now, that's not big news. The Tomahawk 3, the Barefoot Tofino, they use 4 processing pipeline within them. That's common knowledge. But it gets worse. So what do you think about when you think about a switch pipeline? You might have this vision, something that looks like the Super Mario pipe, with a packet coming in, being processed, being edited, and going out through the other side. But that's not how it works in practice. And in practice, it's not green either. What we've got is a bus, and the bus has a width, let's say 256 bytes. As a 512-byte packet comes in the first clock cycle, I'll be processing 256 bytes. In the second clock cycle, I'll be processing 256 bytes. And overall, the throughput will be the clock frequency times the bus width. That's nice. But what happens if I've got a packet of 257 bytes coming in? I'll process 256 bytes of the packet in the first clock cycle. But in the second clock cycle, I'll process only a single byte. This means that I wasted 255 bytes. That's almost 50% of the resources that went down the drain. And to illustrate that, look at the graph. It's hard to point to it from here, but as I'm starting from 64 bytes and need to process about 19 billion packets, and at 256 bytes, I need to process about 6 packets every clock cycle. Then at 257 bytes, I'll need again to be able to process about twice this number. And every time that I reach a misalignment point, the requirement for parallelism will grow again. But let's think. What if we could do better? What if we could ideally push the data into the pipeline, fill the pipeline optimally? If we could pack the data, we could reduce the amount of parallelism required within the pipeline. And the observation here is that for best switch utilization, we should use fixed size data units. And I'll call these data units in this talk cells. So we have got these 4 observations about the use of resources and the scalability in data center networks and in switches. How can we use that? Dramatic pause. So we introduced Stardust. And the idea in Stardust is to scale switch systems to data center networks. And the core idea is as following. Make the network fabric as simple as possible and push the complexity to the edge. We use for that 2 types of devices widely used in switch systems. The first device is what we call a fabric element device, which is basically a simple cell switch. The second type of device is called a fabric adapter. And it's basically a packet switch, very similar to a top-of-rack switch, but with additional functionality of chopping packets into cells. The chipset that we are using in this work is from the Broadcom USENIX, and the devices, Jericho and Ramon, are already the 5th and 7th generations of these devices. And in a Stardust-based network, we are looking at a network that looks a lot like a fat tree. It's basically cloche-based. And we start with packets coming out from the host to the fabric adapter. We're using here standard packets, all the standard protocols, ports that you know, up to the Tor. In the Tor, the packets are chopped into cells. And the entire network fabric, is then using a link bundling of 1. Okay? So no link bundling within the network. Everything is cell-based and without bundling. The second aspect is dynamic cell routing. As we need to send packets from certain input port or certain output port, the cells are spread across all the links that lead to the destination evenly. If I have multiple flows coming in through a certain device, the cells again are evenly and optimally distributed across all the links. And remember, cells here are all of an equal size, so it can provide optimal load balancing. And this is also non-blocking, which is a property of cloche. How do I know how I can reach the destination? Let's say that I have 1 million virtual machines running on top of 100,000 hosts. This means that I'll have 2,500 fabric adapter devices. What I need to know is just the destination fabric adapter. And the entries that I'll have in a reachability table will tell me through which links on a certain fabric element device I can reach the fabric adapter. So for example, to reach fabric adapter number 1, you can use links 1, 5, 8, 14, 36. And this table is being automatically constructed and updated using reachability messages. We provide the information about that in the paper. An important part of Stardust is the use of packet buffering at the edge and a distributed scheduled fabric. So as packets are coming in, they are mapped into virtual output queues in the ingress fabric adapter. Packets can be sent from the virtual output queue to the destination once they get a credit from the egress fabric adapter. What it means is that if I'm looking on a case of an incast, where I have an increasing number of servers sending packets toward the same destination, what Stardust will provide is a fair distribution of the bandwidth, so all the flows will complete around the same time. This is in contrast to other protocols that can have flows that finish quite quickly, while others are being starved. The last property of Stardust is packet packing. So I mentioned that we are using fixed size cells, and we've got a credit. You can send now 4 kilobytes to the fabric adapter. Each cell is 256 bytes, optimally fitting into the pipeline. Now, as packets come in, they are packed into cells. A single cell can contain multiple packets, and a single packet can be distributed across multiple cells. Eventually, the sending is done on packet granularity. So even if you're running out of credit, the packet will finish being sent. To illustrate how this makes a difference, we implement the packet packing mechanism on NetFPGA board, which is an FPGA board. Now, we can't test that on an ASIC because all ASIC are hardwired. You can't test on them the function of using packet packing and not using it. And what we show here is that for a given internal clock frequency of the FPGA, specifically here it's 150 megahertz, using Stardust, you can reach full line rate for all packet sizes. Whereas using a standard packet switch, you will reach full line rate for certain packet sizes that are aligned, but not for other packet sizes that are misaligned. And it's not just for synthetic tests, that's also when you are looking at packet size distributions from workloads such as Facebook, data center, web, and Hadoop. Stardust has a lot of great properties, such as being protocol and traffic pattern agnostic, improved resilience and self-healing, optimal load balancing, and so on. I will not get into those. They are all detailed in the paper. What I do want to emphasize here is that they are all a function of the integration. They are the result of the integration. You can't get everything unless you have all the combined features of Stardust. So for example, protocol and traffic pattern agnosticism are the result of cell switching combined with packing, combined with dynamic routing, combined with fabric scheduling. Take one out, and a lot of those will no longer hold. Stardust requires less network tiers and therefore less devices because it's using a link bundling of 1. But it also saves power and area per device. So a fabric element device will consume 35% less power than a comparable top-of-rack switch. And it will require only 66% of the silicon area compared to the same device. More specifically, it saves 87% of the header processing area and 70% of the network interface area because it doesn't need to support all the different types of marks. This means that if you are implementing building a full data center network, including the edge devices, you will be saving 25% of the power consumption of the network if you are looking, for example, on a 10K cluster. OK, so what I did so far was to say, make the network fabric simple, push the complexity to the edge. But what about the edge? The edge is still complex. I still have the bottleneck that is the top of rack. And what we say here is that for the future, what we need to do is to push the complexity again further. Replace the top of rack, the fabric, what is now the fabric adapter, with a fabric element and turn the NIC into a fabric adapter. The NIC will require a lighter MAC. It will require smaller tables. It will require some virtual output queues, but a limited number of those. And fabric adapter devices already support DMA today. So that's the way forward. In summary, Stardust scales the switch system to a data center network. It uses a very simple cell-based network fabric and pushes the complexity to the edge. It provides better performance compared with the state-of-the-art, lower power consumption, and lower cost. And with that, I'm happy to take your questions.
Himanshu, Azure Networking. So
can you please speak slower, please?
I will try. How does this connect to, for example, your WAN fabric? Like, how do you connect the system that you're proposing to something like a WAN fabric, right? Like you have to WAN, wide area network. You have to reach the internet, right? So somehow, do you envision a Tor having some special stuff for DC networking and some special whole different stuff to talk to a WAN fabric of some sort?
Well, there is a solution for that, but I think that it's better to take it offline because I'm not sure what I can say about that. Okay.
Oh, hi, George Porter, UC San Diego. This is a really, really interesting talk. I really enjoyed it. I was kind of intrigued at the very end. You were talking about, replacing the NIC maybe with like a fabric processor, as it were, and then the Tor becomes a cell switch, which is kind of interesting. But you said that it requires like not that much state in terms of the number of queues. But because of this morning session, wouldn't you need a queue per end host, or even worse, a queue per core on every end host, or every possible number of containers that could run on every end host, or something like that? Like, wouldn't the scale of that be a problem?
So first of all, the way that it is implemented is that if you don't use a virtual output queue, it almost doesn't consume any resources. So it's not like you dedicate a megabyte for each virtual output queue. Okay. And beyond that, you could say, how many active virtual output queues can I have in any given moment? I mean, I won't have 1 million of those. I see.
So is it like sort of like then it's like queue pairs in an InfiniBand NIC or something where there's millions, but you only use thousands at a time or something?
I'm not an expert in InfiniBand, so I'm afraid I can't
answer
that.
Okay, all right, that's very interesting. Thanks.
Okay.
Dmitry Afanasyev, Yandex. You are using packet reassembly and fabric scheduling, and normally it's associated with synchronous system because modular switches are usually synchronous. It's relatively easy to do that. Is it still true for Stardust? And if so, what is the limitation and what are the requirements for the quality of synchronization of the elements? Because in packet switched networks, usually we don't care that much about synchronization of the elements and don't care that much about propagation delay for that reason and can scale it geographically. If you still require synchronization, does it assume some limitation on the diameter of the network physically?
So that's a good question, because the reason that now is a good time to scale from a switch system to a data center network is because now we are talking about latencies that are in the scale of microseconds and not milliseconds. So yeah, that's certainly one of the reasons. We do provide in the paper, let me get to that, a simulation that shows the latency and the queue depths and how we can adjust for variances within the network. But in general, it is because the latency in the data center is constrained and it's not in the order of seconds. Yeah. So it's not for one. I won't implement Stardust in a one.
Yeah. Otherwise, we would have synchronous entire internet, and it's not feasible, obviously. So we are probably talking about hundreds of meters.
Yeah, data center scale. You can think about every 100 meters is half a microsecond one-way delay. Yeah.
Thank you.
All right, let's thank Noah one more time.